All right, so this video is going to focus on the actual examples talking about continuity and discontinuity. So in these particular directions, it says tell where, if any, the function is discontinuous and describe the point of discontinuity. So you're going to have to identify it as non-removable or removable, and then specifically where it is occurring and what type it is. So for 1, if we were to sketch that, we know that x can't be equal to 0 because then our denominator is 0. So x equaling 0, sort of, we know we can't have that. If I sub 1 in, I get 1. If I sub 2 in, I get a half. If I sub 3 in, I get 1/3. And so you're going to have this sort of a curve. If you flip that with the negatives, you're going to find that when you plug a negative in, you get a negative. So you're going to be down in quadrant 3. So looking at this graph with a rational function, we have a vertical asymptote. So this would be a non-removable vertical asymptote, which you can abbreviate VA. So again, you don't actually have to write vertical asymptote, just write VA. So you have a non-removable vertical asymptote at x equals 0. So there are 3 parts to these questions. Non-removable, removable, what kind, jump, whole, or vertical asymptote, and where it is occurring. And those 3 things are going to be checked in terms of when you have to identify this stuff. So just make sure, if it is discontinuous, that you are checking and making sure that you are including all 3 of those items. All right, number 2. So first we look at that function and we say, okay, can I do anything else? Is it simplified? The top is a difference of squares. So what I'm going to do is I'm going to factor that, and I can actually cancel out the denominator. Now, when we talk rational functions, when something gets canceled, okay, if you look at the denominator here, we know that x equaling 1 would not occur with the original function because that would make it 0. But we just canceled it out. So what you have to keep in mind is when you cancel, this is a review from pre-calc and algebra 2, when you cancel, this is a whole. When you don't cancel, such as in number 1, that was a vertical asymptote. All right, so when you cancel, it's a whole. When you don't cancel, it's a vertical asymptote. So we are now left with g of x equals x plus 1. Well, that is a linear function that starts at 1 and goes up 1 over 1, up 1 over 1, down 1 over 1. Now, keep in mind, though, when you pass the point of 1, you have to make sure you leave a hole in the graph. So at 1, 2, you have a hole in that specific graph. So in terms of discontinuity or continuity, this is not continuous, so it is discontinuous, and it is a removable hole at x equals 1. So you have your 3 parts there, removable, whole, x equals 1. For the sine function, if you sketch that, starts at the origin, up, down, backwards, same thing. If you were to put your pencil down on that sine curve and follow it completely along, you will never pick up your pencil. So if you never pick up your pencil, that means that there are no points of discontinuity because it is continuous everywhere. Continuous everywhere. All right, so just because it talks about discontinuity doesn't mean that it has to actually have one. It can be continuous everywhere. All right, 4 is similar to 1. If you look at the denominator, we know that x can't be equal to 6, but it doesn't cancel, which means if it doesn't cancel, we know we have a vertical asymptote. So you go to 1, 2, 3, 4, 5, 6. You can draw yourself a dotted line. And when you sub values in now to the right of 6 and to the left of 6, you will find that your 2 little arches are going to be very similar to what you had in example 1. So now we have a non-removable vertical asymptote, VA, at x equals 6 for that one. All right, number 5. If you look at that function, if you take the denominator and set that equal to 0, you're going to end up with an imaginary number. So we're not dealing with imaginary numbers here, which means there are no values that will make that denominator equal to 0, which means it doesn't matter what x value you sub in, you will always come away with a y value. So you do not necessarily have to have a graph for each one of these, but what you could do is if you know that every x works and every y works, you know that there are no points of discontinuity. Again, the reason being your denominator can never equal to 0, and you can even add that. Denominator cannot equal to 0, so it is continuous everywhere. All right, now number 6, the top is a difference of squares, so we can factor that. And if you look at the bottom, we have two values, x minus 3 and x plus 2. If you set each one equal to 0, you get two x values here. All right, so you get 3 and negative 2, but the x minus 3's can actually cancel. So remember, if something cancels, it is then a removable whole at x equals 3. And if something does not cancel, then it is a non-removable vertical asymptote at x equals negative 2. So you have one of each. You don't just have to have just one. So if you were to plot and sketch this, we have a vertical asymptote at negative 2. So that's our dotted line. I'm just going to keep the 3 in mind so I know that it's got to be a hole there. And you plug values to the left of negative 2 in and to the right of negative 2. And what you're going to find is the image that you get is going to be very similar to 1 and 4. But what you have to keep in mind is as you are dragging this down, as soon as it crosses 3, we said we have a hole at 3, so you have to make sure that you leave a hole there. Okay, now this is not asking for graphs. The graphs are only there to help you and assist you. You do not have a graphing calculator for this, so sometimes a visual is definitely helpful. But it does not require you to come up with a graph with these particular sets of directions. All right, with number 7, so that is a sine function, and other stuff are being done to that sine function. But we know that in 3, a regular sine function is still continuous everywhere. So one of the properties that we had done on page 1, not page 1, sorry, a property states if you really do something to if you keep adding to a continuous function, it's still going to be continuous. We have no denominator that we're working with here. So it doesn't matter what you do to both the sine function or the cosine function, both of those are going to be continuous everywhere. So there are no points of discontinuity, and you can just write continuous everywhere. All right, we have one final one for this set, and then we have a couple more notes to go over here. So this is a piecewise function. There are two pieces here, so something that you definitely could do is make yourself a table, say. So we have one function where h of x equals x plus 1 when x is less than or equal to 0. So I'm going to make a chart. So less than or equal to 0. So that's my x and my y. So we have 0, negative 1, negative 2. That should be enough. And then we have h of x equaling x squared plus 1, where x is greater than 0. So again, make a chart. Now, what you have to keep in mind, it says greater than 0. I'm going to start at 1 for right now, but we are going to have to do something to that later on. So if I sub it in, if I sub on the left side 0, negative 1, and negative 2 into the x plus 1, I get 1, 0, and negative 1. If I sub 1, 2, and 3 into the x squared plus 1, then I'm going to end up with 1 squared plus 1, which is 2, 2 squared plus 1, which is 5, and 3 squared plus 1, which gets you 10. So this is giving you points to work with here. So we have 0, 1, negative 1, 0, and negative 2, negative 1. And this is a line. So this is a linear function going down. So it's going to go this way. And for the second piece, we have 1, 2. We have 2, 5. And let's just say 3 comes up here. And this is a parabola. Okay. And it's greater than 0. So I'm going to have my hooked edge here. But now if you look at that graph, you might say, okay, well, there's a gap. That's fine, but you have to keep in mind, when you look at the two restrictions up at the top, right here, there is an overlap of 0. So when we say x is greater than 0, you have to keep in mind that x equals 0.0001. It works. So you don't want to forget that. So what you have to do is you have to take the function that's not equal to it, which is the second function, which is our parabola, and you need to drag that back to where it would be at 0. So if we had 0 here and we plugged it in, I'd get 1. So 0, 1, but we know it can't equal that value, so you're just going to leave a hole right there. Okay, so whatever function is not equal to in the restrictions that are right here, that's the one you have to drag back and just double check to see where it would be. Don't necessarily just match it up with where the other one ends, because it may not end up there. But you have to drag it back to where it would be when you sub it into the actual chart itself, which we did right here. So according to this, if we put our pencil down and we follow it completely along, if I trace it in green now, if I followed it along, you will find that you are never actually picking up your pencil the entire time, even where that hole overlaps that closed circle, which means that if you are not picking up your pencil at any point, there are no points of discontinuity. Therefore, this is continuous everywhere. Continuous everywhere.